So we have seen the different operating modes of this Npn transistor in common emitter mode. And this diagram is good if we want to understand what is going on inside the transistor and how amplification works. But when we want to study it on the paper, or if you want to convey the circuit diagrams, this is not a convenient way to show the circuit, right? Because it takes a lot of space. So like the PN junction, we also have a symbol for the transistor. So this is the symbol for a transistor. Sometimes they put a circle around this symbol. Both symbols are fine. You can use it without a circle or with a circle, it's up to you. So this is the circuit symbol for a transistor, and it is only for NPN transistor. So you can see that one leg which has an arrow is emitter. That is the identification arrow actually. Whenever you see a symbol, because now you can see like there are three junctions. So if you have a symbol like this, this is base, the um, vertical stick below this horizontal bar, this is base, and then we have a collector, and then we have emitter, like the uh, three connections of a transistor, because we already have studied that it has three terminals. So this emitter and this arrow is showing the direction of the conventional current, but I have been talking only about the real direction of the current and not the conventional one. So whenever you want to use this figure and you want to explain whatever I have discussed, just consider direction of the current opposite to this arrow, because this is an established circuit symbol of the transistor and we can't change it. So whatever is the direction of the arrow, current will flow opposite to it, and you already know that current will flow from emitter to the base. So it will go from emitter to the base and then to the collector, and some current will of course will flow to the base. It depends on the biasing conditions. So whenever I am talking, it should be according to the active mode of the transistor or active region of the characteristics of the transistor. So in the active region, we know that the emitter and base junction will always be in forward bias mode, and base and collector will always be in reverse bias mode, because in other conditions it is either on or off, and we are not interested in that operation because there is nothing special in those operations. Special is when this emitter and base junction is in forward bias mode and base and collector is in reverse bias mode. So whenever I want to show the transistor diagram, I will present this circuit symbol for a transistor because it's easier to understand and it takes less space. But of course, we won't be able to see the internal structure and what is going on. I have already discussed it in detail. So now you understand the operation, whether they are heavily doped, lightly doped, whatever. But now we will focus on to the general operation of the transistor, how the current flows, and we get amplification. That's it. Because the reasons are hidden behind this, behind the structure of the transistor. And we also have a symbol for Pnp transistor. You already know we can make two type of transistors, especially in this case. We can either put N type in the middle and then two P types on the both sides, or we can make Npn transistor like this one. We can sandwich a P type between two N type. It's up to you. And Npn type is the most commonly used. That's why I have only discussed the operation of Npn, and I suggest you to keep this symbol at the back of your mind, but try not to use it at this stage when you are trying to learn the working of a transistor, because it's not good idea to change the conventions every time. Sometimes use NPN and then PNP, because you will get confused with the direction of the current. And it is same, the operation of PNP and NPN is exactly same. Only difference is the biasing conditions and then flow of currents. Just think everything opposite. So at this stage I suggest not to think about PNP. First get all the concepts and working and everything in your mind of the NPN transistor, and when you get to understand it very well, you can think how a PNP transistor works. So the only difference for a PNP is the direction of the arrow is now reversed. And once again, this is conventional current. So according to my convention, which I have been using during these lectures, is the real current. So real current will be in this direction. Always keep it in that mind. And I also suggest you that whenever you are trying to answer the questions related to transistors, PN junctions, or whatever, always mention that I am taking the real direction of the current. And conventional direction of the current should be opposite to what I am describing in the figures or in the answers, so that your examiners knows that you are talking about the real direction of the current. Otherwise, he may think that you have a wrong concept of the direction of the current, because if he has in mind that we will only consider conventional current and everything you will describe will be opposite to that one, so he might think that you have a wrong concept of the direction of the flow of the current. So always mention it everywhere with a note. Write a note and write, I am taking the real direction of the current. Now let's draw the circuit diagram of a transistor in common emitter configuration, because you have seen everything in this figure which I made for you, so that you understand what is going on inside the transistor and the reasons behind each and every function. But now we will draw a circuit diagram, and here is how. So you know that this is a symbol for NPN type transistor, which I used in that discussion before. It is Npn transistor, and the symbol diagram for this Npn is here. And now I will just compare both figures and draw the circuit diagram. So I will see here. So in this type, I connected the collector with a positive terminal of the battery. So I will draw a circuit diagram according to that. So collector is connected to a positive terminal of the battery. So here is the collector. So I will go this way and then this way. And now I will realize this circuit in with the practical applications. So I will connect it with a positive terminal of the battery, and you know that we represent positive terminal of the battery with a longer bar, and then we have a negative terminal, and it is not negative, it is ground. But you know that the positive and negative are just relative to each other. Then in the common emitter mode, we know that emitter is always at ground level. So let me show you the real figure that you see here is the emitter. This is emitter, the left N type, and this is connected to the ground here and also ground here. But in the circuit diagram, of course, I will show the optimized circuit diagram. I don't need to show irrelevant or some extra terminals. It will just produce some confusion. So this one is ground, and this is how we show ground, and this ground is connected to both here, and then it will be connected to the base. So once again I will take base, and then I will show you why I'm leaving these blanks. And once again let me see the real image, that this base is connected to the positive terminal in this situation of the power supply. So, and then the ground is once again connected to the emitter, because this configuration is common emitter configuration. So once again here is the positive terminal, and then I have negative terminal, and of course this the ground one. So, and this is once again connected to the emitter. So emitter is common to both. It is connected to the collector through some components, and then it is connected to the base through some components. And because you know, when we want to find the output characteristics of a transistor in whatever mode it is operating, we want to measure different things. For example, we want to see what is the collector current, right? So whatever current is flowing through the collector in this situation, IC, we want to measure this current, right? Similarly, whatever current is flowing through the base in this direction, we want to measure it. So here is IB. Similarly, we have IC, and that IC is in this direction because I am only considering the real direction of the current. So don't get confused with this arrow because this is showing the conventional current. Conventional current is just opposite to what I am describing here. So here is IE. So if we want to measure a current, we need some instrument to measure the current, right? When we want to draw the output characteristics, or for whatever analysis we are using, or whatever application of the transistor is, we want to know how much current is flowing from the collector, how much is coming out of the base, and so that's why we will put an emitter here to measure the current. So that's why I will make a practical circuit diagram of the transistor in common emitter configuration. Sometimes we need a resistor to limit the current, because if the amount of current is too much, then we use a resistor in series. So of course you may not need a resistor, but whatever. We can give it a name like resistor at the base. Similarly, we can call it resistor at the collector, something like that. And of course, we also want to measure IB, mean current coming out of the base. So here, once again, we will put an emitter, which will tell us how much current is coming out of the base. Of course, this is positive terminal. This is also positive terminal. Here it is ground and ground. And this emitter is grounded, and it is because this is common emitter configuration, so emitter is grounded. And then we want to know the voltage V, for example VCE. If you remember my discussion about output characteristics, so we want to see what is the voltage between collector and emitter, this voltage. So if you want to know this potential difference, we need to connect a voltmeter, and voltmeter is always connected parallel between two terminals. So this will tell me the potential difference between the terminal C, which is collector, and emitter. So I will connect this voltmeter here. Similarly, I also need the voltage BE, which is the voltage between base and emitter. And for this, I need a voltmeter here. So this which will tell me the voltage between B and E. And this will tell me the voltage VCE. This one will tell me the voltage BE. And as you know that collector current is greater than the base current. For a small base current, you will see a huge current or amplified current at the collector. So you have to be very careful when you want to use an emitter to measure the current, that this emitter should present values at least up to milliamperes. But for the base current, you need an extra sensitive emitter which should be able to show or display the current in micro ammeters, in microamperes. And you know that we will need to change the voltages. But for example, when I apply a certain voltage between base and emitter, you know that for each voltage BE, for example, here we have already discussed it, that I will start this voltage BE across this B and E. So I have this power supply. So first I will set this this voltage between B and E to 0. and then I will increase to 0.1, maybe 0.2, 0.4, 0.5 and 0.6. Then of course at 0.6 you will see some current flowing through this emitter, and of course this current is very small in microamperes, and that is the input characteristic. Then you need to change this voltage so that you can vary it, and you know why the current will start rising after 0.6, because that is the potential barrier between PN junction at PN junction. And after that, because now it is in forward bias mode, current will start increasing after crossing 0.6 potential difference between B and E. So that's why you will need to change. So we need to show like an arrow here. It will show that this is a variable power supply, because it means you can change the voltage according to your desire. Similar once you have the input characteristics, and at that time you will fix, like we have discussed here, that before doing that you will fix the voltage VCE. It is a choice, you can put it to 20 volts, but you have to fix it before drawing the input characteristics. You can draw different curves. For example, at 20 the curve may look like this if the VCE is at 20 volts. So it means you also need to change this voltage, right? So I will just present it with an arrow. Arrow means this is a variable power supply. I have the choice to change this voltage. So you know that I will set it this voltage to 10 volts, for example, and then I will change this voltage from 0, 0.4, 0.6, and I will measure this relevant current. So I will make a table. I will put voltage, and then in the next column I will put relevant current, base current IB. And then I will have my input characteristics. This is IB, so the values in the table here are IB, and here I have the voltage value, so I will get a current. And at this time when I am measuring these two values, voltages VCE and IB, I will fix this voltage VCE at some certain value, 10 volts or 20 volts, and of course the curve will be different, but it should be fixed when I am measuring these values, these voltage values and relevant current values. So this arrow will represent that this is a variable power supply. And then I will draw the output characteristics of the transistor. And for that, because now I have input characteristics, so I know the current values here. So for each time when I want to get a value, I will fix the VCE. For example, I will start at 0. So I will set this voltage at 0. And I will do it after recording all the input characteristics, because now I know. And I will fix a base current. For example, in this situation here, so I will fix a base current maybe at 10 microampere. So from the input characteristics, I know that 10 microampere is somewhere here. And if I go here and just assume that I fixed VCE at 10 volts. So when I am here and then I will go down, it will tell me the voltage, that at what voltage I will get this 10 microampere current. So after recording this data, this voltage, I will go back to the circuit. And now I will fix this voltage so that the current is 10 microampere. Now after fixing this voltage, and as a result of this voltage I will get 10 microampere current. This is the base current IB. Now I will vary this power. I will start from 0 and then maybe 1 and then 2, and for each time, for example for 0, I will record the value of this current, which is IC. Then I will change this voltage to 1. I will measure the next value of current, whatever it is coming from this emitter. Then I will change to 3 and then measure the relevant current value. So because and from this table of values I can draw this curve, the first curve, which is, and at this time remember the base current is fixed at 10 microampere. So from that table I will get this curve, and it shows that actually there is no change in the current of collector, the current coming out of the collector, no change whenever I am changing this voltage. You see, it is very interesting to see that almost there is no change in the current, whatever is the voltage between collector and emitter. But the astonishing thing is that this current, when for the base current 10 microampere, the corresponding collector current is in milliamperes, and we just saw it, like it can be the amplification factor beta, it can be 170 times amplification of the base current. I mean, whatever is the base current, amplification can be 170 times of the base current at the collector current, or it can be even 150 times. It depends on the transistor and situations. So with this beta factor is the amplification factor, or current gain, because for a small base current we get huge increase in the current at the collector. Similarly, the next you will find that at what value, for example, if the first time you set the base current at 10 microampere, now you may choose to set it at 20 microampere. So you will use this input characteristic curve to find the relevant voltage, that at what voltage you get this current 20 microampere. So you will note down this voltage, then you will go back to the circuit diagram and you will set this voltage, whatever value of the voltage you saw from the input, so that you could get this current now 20 microampere. So now after setting this voltage, and of course after, as a result of this voltage, you will get this current in microampere, 20 microampere. Now you will not disturb anything here. Now you will come to this part, and now once again you will fix this voltage to 0, and you will record the relevant corresponding current, collector current in milliamperes, of course. Then you will fix it to 1, and you will measure the current, collector current, and you will make a table, and then you will draw that the values of those tables here. That will be the second curve. The second curve is when the base current is fixed at 20 microampere, and once again you see that actually there is no effect. Whatever you change the voltage between the collector and emitter, current is same, and of course current is different this time because the base current is increased. So you can see that the whatever you fix the base current, the collector current is amplified proportionally. I mean, for when it was 10 microampere, you saw there was a huge increase, almost 170. The current gain was 170. And when you increase the base current little bit, the corresponding collector current is also increased, right? So whatever you are increasing the base current, and collector current is also amplified proportionally. And you can find that with this beta function, we call it current gain. So you know the current IC, mean the collector current, and you already know the current base current. Just take their ratios and you can find the amplification factor for each of these curves. So this is a realistic circuit diagram. So if you are asked that draw, or how can you use an NPN transistor or just any transistor as an amplifier, you can present this circuit that this is how the current is amplified. And current is amplified in common emitter mode. This is common emitter mode, and it has a current gain. So this setup which I have just discussed is a setup which can be used to have current gain. When for a small base current I get a high current at the collector. So this setup is basically made for current gain. So here I have applied this power supply with the collector and emitter. So we sometimes call it VCC, that a power supply which is basically connected with the collector. Similarly, this power supply which is connected with the base, we can label it as VBB, a power supply which is basically connected with the base, and we get a huge current gain in this setup. Now my question is, here we are using we are basically using it for a current gain. But now next, what if I give a sinusoidal voltage signal at the input? It means that I connect this sinusoidal input signal here across the base and emitter junction. So I can call it V in, this input signal which is changing with time and is a sinusoidal voltage signal, and I apply it across the base and emitter. So here we have once again VBB, and now I don't need emitter or the voltmeter because now voltage is changing, you know that, and even I don't care about the direction of the currents because it will fluctuate back and forth one, and so I remove those components. And here is the output signal. So as you know that in common emitter configuration I can call it V out. So you see, even when I give a sinusoidal voltage signal across the base and emitter, I connect it with this one, this sinusoidal voltage, I will get an amplified voltage signal at the output when measured between this resistor, one end of the resistor, and then from the other end or the emitter. So between collector and emitter, I will get an amplified voltage signal. If I give a sinusoidal input voltage signal between, I apply it between base and emitter, I can get an amplified voltage signal at the output, means between collector and emitter. Wait a minute. I can see that this voltage signal is amplified, but the shape is different. It seems like it is when it is up for the positive half cycle. For example, this one, I see that this height here the same, or of course signal is amplified because this peak value or the height of the peak is greater than for the input. But it seems like for the positive half cycle, I get a negative half cycle at the output. And for the negative half cycle at the input, I see that I get a positive half cycle. So although signal is amplified, I can see that, but it is 180 degrees out of phase. So this is what you will get. If you give an sinusoidal input to the common emitter transistor, you will get voltage amplification. Voltage will be amplified, but it will be 180 degrees out of phase. So this setup is for voltage gain because here we are amplifying voltage. So a transistor in common emitter mode, we can use it either to amplify the current, we can get current gain, or we can use a voltage gain. And if we apply a sinusoidal voltage input, we get amplified voltage output, but it is 180 degrees out of phase. Common emitter configuration is not the only way we can use a transistor. There are two other ways as well. The one of those two configurations is common base configuration. And now it's easy to visualize that in common base configuration, the base will be grounded. So it will be connected both with the emitter and collector through the ground terminals. So I can rotate the power supply so that the ground terminal is towards the base so that I can connect it easily. So this ground will be connected with the base. Similarly, this base will also be connected to the ground here. So if the base is connected with the ground, now we have to decide to which terminal should I connect this n-type emitter side. As you know that emitter and base junction should always be in forward bias mode, and base and collector junction should always be in reverse bias mode. So let's see the first junction, mean the emitter base junction. We have to make it forward bias, and we know that base is at ground. So if base is at ground, and we know to make a PN junction forward bias mode, we need to connect N type with the negative and P type with the positive terminal. So if the base, which is P type semiconductor, as you can see, because I am considering only Npn transistor, so the only way I can make this junction forward bias is to connect the N-type emitter with the negative terminal, because only negative is at the lower potential than ground. Ground is at 0. You can consider it 0 volt potential. Then of course the N-type will serve as a negative. So I will connect this negative terminal with the emitter. So now this junction is in forward bias mode. To make the base and collector junction reverse bias, and we know that collector is N-type, so I have to connect it with a positive terminal, because if N-type side of a PN junction is connected with a positive terminal and P-type side is connected with a negative terminal, then this junction will be in reverse bias mode. So now P-type side is connected with the ground, and in order to make it negative, I need to connect the collector with a higher potential. So it means I have to connect the collector at a higher potential or a positive V, because then positive will be at higher potential, so it will serve as positive and ground will work as negative. So N-type side is connected with positive side of the power supply, and P-type side is now will serve as a negative terminal. In case of the emitter, it will serve as positive, but in case of collector, it will serve as negative, because now it is at lower potential, and lower potential is like negative potential. So now it is working in active mode, and now you can imagine that how the situation will go, how the current will flow, and you should be able to understand the mechanism which will go on, just with a little bit difference. Next, we can see how to draw the circuit diagram, of course, because I told you this figure is not very practical to draw on the papers and discuss different configurations. So here I have a Npn transistor, and I want to draw the common base configuration. As usual, base is always grounded. Then collector will pass through a resistor. This resistor is just to limit the current, just in case we need, so we can call it RC. And then it will go like this, and we need to know how to connect the terminal. So we have decided that this collector should be connected with a positive terminal, so I will put a positive terminal and then a ground, and it will be connected with the base. Emitter will also pass through a resistor, and I can call it RE, the resistor connected to the emitter. And as we decided that the emitter should be negative, and then the other side should go to the ground. We can call it VCC, and this is VEE, the power source connected to the emitter. So you should be able to understand the output characteristics of this configuration. So before ending this lecture, I want to tell you that common base configuration is commonly used for voltage amplification. And the good news is that when you give this input signal, sinusoidal inputs voltage signal to this configuration, you get an amplified voltage signal. And the good news is that this is not 180 degrees out of phase. So the phase of the output signal is same with the phase of the input signal, and of course it is amplified. And for the common base configuration, we have amplification factor, which is called alpha, and it is the ratio of collector current divided by emitter current, because now base is grounded, so we don't care about the current of the base. So now this is the ratio of collector current divided by emitter current, and this is called alpha amplification factor for common base configuration. Please read your textbook, and I am sure you should be able to understand everything for this configuration as well. I don't want to repeat each and every step again and again. And if you don't understand, then please watch my lectures, previous lectures again, because I gave a lot of detail, a lot of the discussions on the working of the transistor and PN junction and many other things. Because if you understand those concepts very well, it's easier to understand the next steps, because a transistor is just an extension of a PN junction, and there are different modes. Moreover, you should also be able to understand that what is the saturation mode and what is the cutoff mode for even common base configuration. So you may try to answer to see like when it will be in off state and what are the conditions when both the junctions, mean the emitter base junction and base collector junction, are in reverse bias mode, and when both of these junctions will be in forward bias mode, and you should derive those conditions as well.